Hello, everybody. Hello. Welcome back to the Flare Educate series. This is session number 6, or to put differently, week number 3 of the Flare Educate series. So far, we've covered a bunch of things about Flare. Well, week number 1 was actually dedicated not to Flare specifically, but to blockchains in general, to smart contracts, to EVM, and then from week number 2 we kind of dived into Flare, and our last speaker, Anthony, provided an overview of what Flare is, of different protocols of FDSO, of FDC, and so on. And today we are joined by our second speaker, Filip, also from Flare, who will be covering this session and two sessions next week. Today, Philip will be diving into the Flare data connector more in detail than what was covered last time, and he'll also have a technical demo on how to use it. So without further ado, Philip, feel free to start sharing your screen. Welcome to the stage. If anybody has any questions, you know where to put them in the questions tab on the chat, and Philip will get to them in due course. Without further ado, Philip, the floor is yours. Feel free to introduce yourself and start the session whenever you are ready. Good luck.
Okay, hi, thank you, Nivan. Welcome to the session 6. We're gonna do a deep dive into the FDC. We're gonna dabble in some code. We're gonna prove something on Ethereum. We're gonna see what else you can do. And this is a really good preparation to see what can happen with FDC in the future and what you can do with it, how you can use it, and pretty much how you can enhance your blockchain use, how you can empower your blockchain applications to do a bit more than just issue tokens and show pictures of cats. So I want to keep this as active and as interactive as possible. So if you have any questions, I have the rest of the live storm opened here. So don't be afraid, just shoot them in and I'll answer them pretty much during the presentation if I can, or leave them out for later. But the easiest thing is to pretty much clarify things immediately once they arise, so that anyone can hear what you're thinking about and everyone can pretty much participate and see what's happening. Okay, so FDC, you've covered this and a lot of other topics previously with Anthony. So you know that Flare is a blockchain for data. You know what does this mean. Because you're here, you also already know why you want to do something on the blockchain. As, for example, doing something in an alternative presentation when you would do it on a single server, when you would do it on a bank, when you would do this as a mobile application. But if you've selected the blockchain as the medium as to where to pretty much have your application, where to host it, and where to distribute it, you know that blockchains are designed to be secure. And the main purpose, the main thing you have from it is the ability to verify the whole chain of computation from block 0 to block n independently, irrespective of what has happened. So that anyone can take blocks provided by some validator, some RPC node, validate them on their own, make sure that they're correct, and then operate on top of it. So there is no central authority you have to trust, and there is nobody that you have to fully trust, or there's nobody that you need to perceive as trustworthy enough to start with their data there. So that's the whole point. And the main problem we come to, and the main problem we've pretty much been solving at Flare, is what you do if you want some data from the outside. The first question you have to ask yourself is, why do you really want the data from the outside? Well, fact is that if you have applications, if you have dApps, if you have projects that are operating in isolation, so they can't touch anything from the outside, those applications are very, very much not dead, but they're not that useful. The main thing is that if you can only access things on your blockchain, you're very limited. But by opening your dApp, by opening your project to the data somewhere else, as you've seen in previous time, initially with the FDC or with the FTSO, you know that now you can gather more things, and people are always eager to use something more in their application. People are eager to connect their application to something useful, to something real. And the main thing here is security. So there is a bunch of things you have to think about. The standard Oracle problem. So how do you know that this is secure? How do you know that your data is coming on time? How do you know that your data can't be tampered with? And in that case, you really want to make sure that your applications are relying on the data that is as secure as the blocks itself. So you need to make sure that the whole stack you're trusting, think of a security, think of your data acquisition process and your execution as a chain. You need to make sure that all these pieces of chain are really as secure as possible, because if you have a small piece of chain that is not secure, this is when the problems are going to arise, and this is where attacks are going to happen. And the main thing with this is that security acts as some sort of an insurance. You don't need it until there's a turmoil somewhere, when somebody has a lot of money invested, when there's an incentive to do something bad, and at that point, you're going to feel the pain of this insecurity. Before that, it's going to all go smoothly. So you have to bake security in it from the beginning. Otherwise, it doesn't really make sense to be on blockchain. That's for the initial philosophy. But yeah, so from FTSO to FDC, I'm just going to repeat in short the things that you've already heard, just to kind of refresh your memory what FDC does. So FTSO allows for probabilistic data, prices, temperatures, amount of people, things like this. FDC allows you to ask questions and get responses about concrete data points, concrete yes-no questions, and concrete deterministic attestations. Why is that useful? But that is useful because sometimes the data points you need to access, the data you need to use, is not really the data that you might get in a deterministic sense. So for the price of Bitcoin, it's fine if it is 90,000 or if it is 90,000 and a cent. That's pretty close. But if I'm saying, okay, can you make sure that account A has transferred some funds to account B, and you say, yes, account A has transferred some funds to almost account B, where B is a bit off, or I don't know, 2 bits off or stuff like this, that's not really that useful if you want to issue this, if you want to issue something on top of this payment. So with FDC, we're solving a problem when you need to have an attestation about a concrete thing when there's no near miss. It's either correct or incorrect. Everything that is not fully correct is incorrect and not useful. So FDC is solving this. And so what it allows you to attest about a specific data point. And the main thing, the security part, is it uses a network of attesters. And this network of attesters pretty much verifies whatever you've asked them before. So it verifies that you've asked them, you ask them, okay, did this payment really happen? And all those attesters execute the same query, either on their Bitcoin node, either on their Web2 data source, either on the Ethereum node, say yes, validate this, and provide this on network. And the main security result you get from this is the fact that the data providers here are same as validators. So everybody that's attesting to this is also producing new blocks, is also producing FTSO prices. So all these points in the middle are made sure in such a way that the whole chain of security is secured on all levels, from block production, data acquisition, computation, consensus, everything. So everything is intertwined. So this is the case where we have this multi-security model when our validators pretty much double as data providers, as attestation providers, and all this, just to make sure that everything works correctly and there is no small points of network that can easily be attacked and can be problematic. And importantly, we provide you with some initial data types. What are those initial data types? We're going to cover some of them, but initial data types are the few that we're going to see today. But by a consensus, pretty much by offering some additional incentives to data providers, we can also add new data types pretty much through the vote. So you offer an incentive, please, would you support this new chain, this new data type, this new way of attesting? You say, you provide some incentive, you explain what this attestation is, you provide a fully deterministic description what it is, and the data providers can choose to support it or not. Okay, how does this work? So I think that's the last slide, yeah. And we're gonna go to a bit more useful things. So Flare Data Connector, how does this work? To make things as efficient as possible, we proceed in multiple steps. And today you're gonna be doing a bunch of things with code. Let me just do something. Just a second. So Flare Data Connector allows you to attest to specific points. So what you do is you proceed in a series of steps. So first thing you do, you observe a data point that you want to later prove. So let's say you have a Bitcoin transaction or an Ethereum transaction that you want to prove. You say, okay, this is the transaction I'm observing. This is something that I want to bring to chain. And the main question that you have to ask yourself is why? Why do I want to bring it on chain? Well, the reason to this why is your debt. The reason to this why is your project. The answer to this why is because you need information from it. So let's say somebody is paying me on Bitcoin. I firstly observe this Bitcoin transaction. I know that this is the transaction I want to use. And now I'm going to use this on Flare. And there's a process how to do it. So firstly, I see that something has happened that is of interest to me. The next thing I do, I use the Verifier server to now prepare a request that will allow me to issue this request to FDC protocol, to FDC, which will then kickstart the process of data providers verifying this. So I go to the Verifier server, I send this data that I've observed, pretty much a consolidated piece of it, just a hash of this Bitcoin transaction and who I'm observing. And this Verifier server responds with a prepared request that can then be easily picked up by the FDC. So you could do this manually. It's pretty much just encoding things. But it's always easiest to just use a tool that's already provided. And the Verifier server does one more thing, which is apart from just preparing the request, it also prepares the MIC, so-called MIC code, message integrity check code, which allows you and all the FDC participants to quickly verify if they have arrived to the same conclusion as you. Because we're talking about deterministic things, what you're doing is you're effectively saying, please provide me with information about this Bitcoin transaction, and you already know what this information should be because you've seen it. It's known. There's no way to answer this question differently. And the verifier pretty much hashes this and said, please provide me a response to this question. And this is the response I want to get. This is the response I'm currently getting. Please confirm it. It's just that you're not providing a full response. You're providing a smaller piece. Okay. Once you have this request, and we'll see the request is not that complicated, you submit this as an attestation to FDC protocol. This is the first thing you do on chain. You now submit this on chain, an event is emitted, and all these data providers from the previous round, so the validators, the data providers, now pick this up, execute the same query as the one you did through the Verifier server, see the same data, match it to your MIC. They make sure that they're seeing the exact same thing that you said they were supposed to see. And if they can, they say, okay, we can do this. This goes through a bit vote to select the most optimal bit set of which attestations we can prove in a current round. And then this gets pushed to chain. How does it get pushed to chain? Well, there are a few things we need to make sure. Firstly, as you already know, you do not want to push a lot of data to chain. Why? Because if you're pushing too much data to chain, the chain becomes slow. You put too much pressure on your validators. You have to pay them large amount of fees. And we've all seen these problems in other chains. What you want to do is the following. You want to push on-chain just specific bits of information that can later be reused while still allowing you for the full security assumptions we had from before. So what do? All these attestations from a single round, the round lasts for 90 seconds, are put into the Merkle tree. A Merkle tree is just a tree of Merkle leaves. They're put into a Merkle tree, and this Merkle tree gets connected together. You get a Merkle root at the top, which pretty much consolidates the information from all the leaves, and this Merkle root gets deposited on-chain. So instead of the whole data set on-chain, we only get one Merkle root. That's much more efficient, but it still allows you to quickly check if the data I'm holding in hand was in fact correct and was in fact confirmed by the FDC. And now it's my turn again. So I've submitted this. Data providers have come to an agreement. We'll see how that works. And now it's time for me to get the full data together with the proof that this is indeed what the data providers wanted to have. I get this through the DA layer, the data availability layer. I request the proof. I get back proof and full data. And once I get this, I have all the necessary information. Again, off-chain. And with this necessary information, I just invoke my contract and say, okay, please, I'm sending you these data points, the things that are important to me, together with the proof that asserts that this data was indeed included in the Merkle root of the correct round. What this means is that the contract at the end has access to full data at a very cheap level. So it's not saved on chain. The only thing that's saved on chain is what you need, but can always verify that the data I'm providing it is indeed correct. Even if the DA layer were to lie to me, even if the DA layer were to be malicious, the contract can quickly verify this and say, nope, you're providing me some malicious data that was not attested in the FDC. You can't say this data is correct. You can just say this data together with this proof is correct or incorrect. So if the DA layer is malfunctioning, I can always regenerate this. But I'm always sure that bad data cannot come into my contract, and I can easily verify this. And just a few more things before we go to the code. We currently support 6 different types. We'll go through them. They're nicely described in the specification. They're also nicely described in the dev docs, which you are more than welcome to check, because you're going to be using quite a lot of them on the upcoming hackathons. And those are EVM transaction, so information about a transaction happening on an EVM network. We currently support Ethereum, Flare, and Songbird, so that we have full interconnectivity between them. And importantly, we'll see EVM transactions not only contain the amount and the transfer amount, but they also contain all additional events that have been emitted. And then we have 5 additional things that are available on UTXO chains and XRP Ledger. So all those 5 different attestation types are available on Bitcoin, yeah, Dogecoin, and XRP Ledger. And they are specifically tailored for some more financial heavy duty things and F assets. One of them is payment. Payment is very simple. And payment pretty much says, okay, can you confirm that the payment has happened on a specific chain and a payment has been executed? Oh, I see some questions. I'll answer them just after this. So a payment has happened and you get full information about the payment. Who paid how much, at which specific time, how was it confirmed? Then you have address validity. Address validity is interesting because it's not that data heavy, it's computation heavy. So let's say you have a specific Bitcoin payment, the Bitcoin address, and you want to check if this address is valid. Doing this in Solidity is feasible, but it's not something you should be doing, and it's not something you would like to do because it's quite complicated. You have to go through the full specification. You have to implement it. There's a bunch of health checks and sanity checks, and you have to implement all this. So doing this is expensive on chain and can be problematic. And these attestation types allow you to pretty much say to the network of validators, can you calculate this part for me, return me the result, and then I can use this on chain. What this means is you can combine this with payment. Somebody is saying, okay, please pay me this much on Bitcoin to this address. And the first thing you do is say, okay, but you have to provide the address validity proof. So you have to provide me with the proof that this address is valid. And it's easy. They initiate the FDC round, prove the address is valid. And it's easy to say, okay, please initiate the payment to this address. You can see it was proven via FDC that it is already valid. And then you have confirmed block height exists. Confirmed block height exists allows you to check how the other networks are progressing. Let's say again, I want to pay you something on Bitcoin, but I want to first make sure that the Bitcoin is in fact progressing. There's not, I don't know, the network is not stale. The network is producing new blocks. This confirmed block height exists, allows you to check how the network is progressing. And it's pretty much the following. So I'm proving that Bitcoin has block number XYZ, and in response, I also get back, yes, it does have it. It's not the latest block. There are X new blocks on top of it. And the block production rate in the last Y seconds is this amount. So you can see how the network is progressing, and you can easily prove things. Then there's balance decreasing transaction, which is a bit more complicated and used within F assets. Balance decreasing transaction allows you to check that a specific transaction has decreased the balance. Think of an application where you would want to have some sort of a vault on Bitcoin or on XRP Ledger, and you would say, okay, please hold these funds in that specific vault. And with the balance decreasing transaction, you can always observe if there was a transaction that changed the balance. There are multiple ways to change the balance, but you don't want to know them. You just want to know that there is a way for FDC to prove this to you. So whenever a balance has decreased, FDC is able to prove this. You request this proof, and you can prove that something is doing something funky. You don't really have to fully know which type of transactions you have to watch out for. This is done by the FDC, by the protocol. And then there's the reference payment non-existence, which allows you to prove that something hasn't happened. So combining payment, address validity, and reference payment non-existence, you can say, okay, I'm going to pay you something on a valid Bitcoin address, and the other party can prove after a while that you have either completed the payment, or they can prove after a while that you haven't completed the payment by pretty much saying to the FDC, can you check this piece of Bitcoin code and see that there was no specific payment made? Pretty much think of your utility bills. They can prove that in the last month you haven't paid them with that reference, thus executing something new on Flare and say, look, this hasn't happened. Let's slash some collateral. Let's, I don't know, not issue them a token, whatever. Okay. Todd is asking, in this multi-security system, which part do you think is the least secure? There's an evil question to answer this, and there's a non-evil question to answer this. So an evil answer is it's always the human. So whenever you have validators, whenever you have anybody doing something, it's always the human that's interacting with your dApp, or the human that's building your front end. So from a purpose of the whole dApp status, from end user to other end user, I think the biggest security issues are mostly on front end, when you can have a bunch of problems with it. Within the purpose of Flare as such, within the purpose of the blockchain, if we disregard all the necessary things, I think the biggest security risk is making sure that the validators and the data providers are not colluding, so that they're really using different things, different infrastructure, different servers, different implementations. So making sure that in parts, when you really want to be decentralized, you are actively pursuing this decentralization. This is not a easy thing to achieve. So we've gone through multiple iterations of management committees, how to make sure the data providers are correctly answering queries, how to design the protocol in such a way that you can't copy that much, so that you really have a wide network. But yeah, it's this factor of knowing that this last data acquisition part really is handled by the whole network, otherwise than just a few trusted parties that everybody else copies. So I think this was one of the most difficult things we had to overcome. And this is the one that breaks the easiest, specifically if you look at some other protocols, when they quickly collapse from a huge set to a much smaller set of trusted parties, which is just easier to work with, but it has a bunch of problems. And there's a question from Theo. Are there any new attestation types expected to come? Yeah, apart from those 6 we currently have, we're preparing one that's going to be live on testnet, but really just for testing, that's going to allow you to query arbitrary Web2 data sources, arbitrary Web2 APIs, and process them however you wish. So that's one that's really going to enhance the ability of FDC to add new things, but we're still developing it, because the main problem is you have to make all these deterministic. So with Web3, it's easy to say, yeah, has this happened on Ethereum? With Web2, you have to think of a bunch of new problems. So what if the API I'm looking at is behind the API key? What if it is geographically locked? What if something changes randomly? So how do you achieve consensus on top of this? This was a huge problem, but this is going to pretty much expand what you can do with this by a lot. So think open banking, think weather APIs, think assurances about proof of reserves and stuff like this. So there's a bunch of things you can do there. And that's coming to testnet pretty soon. So we're testing it on a hackathon. We've already tested an initial piece of this on Encode's hackathon at the end of October, and it was quite successful. So that's why we decided to include it in the next iteration. Okay, so today we're going to take a look and execute a proof of Ethereum transaction. So EVM transaction, we're just going to follow this schema. So it's going to be simple. We're going to find an Ethereum transaction. We're going to prepare a request. We're going to submit it. We're going to wait for a while. And then we're going to use the response to prove something on chain. We're going to create our smart contract. And we're going to see how easy that is throughout the library. So enough babble. Let's get some code ready. Okay, so this is the code. I'm just gonna push this down. But before we go to fully see the code, let's find us an Ethereum transaction. So there's a strict separation on Flare when developing between test nets and real nets. And since we're going to be operating on test nets, we'll have to take a transaction from Ethereum Sepolia. So the easiest one to take. Okay, let's just wait for the Explorer to load. And while we're waiting for the Sepolia Etherscan, I'm just going to take this old one. I'm just going to take the old one since I can't get the new one yet. Okay, so this is an Ethereum transaction that does a bunch of things, but most importantly, it emits some events. So the huge information treasury you can get in Ethereum transactions are those events. Why? Because you can track moving of funds, you can track what contracts are doing. You don't have to execute them. Pretty much the only thing you need to know is what they think is important to the external world, and that's the only thing you really want to use from Ethereum transactions. Sure, funds are fine, transferring funds, who's doing what, but events are really the bread and butter of core Ethereum data-rich systems. Okay, and Ethereum transaction, what does it do? What does it tell us? The easiest way to see this is to go in the spec. Where is it? Attestation types, Ethereum transactions. So all this is linked in our dev doc, so you can easily look at them yourself, take a look at what they do and so on, but we're just going to go through it quickly. So I have to provide transaction hash, some confirmations, inputs, and those two are important. I can say, please list events, and I can explicitly list which events to list, or just provide an empty list and say, okay, include everything. And in response, I get a bunch of things about this Ethereum transaction. And most importantly, I get these events. I get a list of events emitted by this transaction. So if I go back to this Sepolia, which is probably not going to load, I don't know why, it just doesn't like me. I can see this event. So if I execute this, I would expect to get 4 events back just for this specific transaction. And those are really the bread and butter. And what do events tell me? When they tell me a log index, so where was the event included in the block, emitter address, so who emitted this event. This is important because if you have a transfer event from a token, this is the one that you want to use. So do I have USDT transfer event? Yep, that's important. Do I have some shitcoin transfer event? I don't care about it. Topics. With topics, you can determine which event it is and which things are important, and some additional data at the end of the event. So for example, here we have a transfer event from ERC20 token, transfer event, topic 1, topic 2, to and from. So who was the sender, who was the receiver, and the value of token that was transmitted. And topic 0, that's an important one. Topic 0 is usually, at least when compiled with Solidity, it's the signature of the event. That's not necessary if you write YUL or if you write assembler directly, but this is very useful for selecting things from Solidity contracts. So you should keep this in mind, but this is pretty much the thing you use to disambiguate between different events. And then you have some additional value, which is nicely decoded here. Okay, let's take a look how this looks. So we're here on a FDC verifier for testnet that's provided to us by Flare. So we're providing a bunch of this infrastructure. This one is guarded by an API key, which you can get from here. I'm just going to show you. The API key is not that big of a secret. It's also available in the repository. But this endpoint is rate limited. So we're providing you with an API key that's easy to get, but it's rate limited, so you do not abuse it. Okay. So, timeout on Cloudflare. Shame. So we're going to use the old one. Doesn't matter. That's an important thing with the verifiers. They're decentralized. They already know that they're running their own thing. So even if the Sepolia scan is down, we don't care. Okay. So prepare a request. Let's see how that looks. We're going to try it out. I'm going to input my transaction ID. Have this empty. Require just one confirmation. Execute this. I'm going to get an error because I'm working. So this thing here says the source is Ethereum, but I'm not going to work on Ethereum. I'm going to work on test Ethereum, which is Sepolia. I know that this might look scary, but it's actually very simple. So this thing is just hex encoded test Ethereum, and attestation type is EVM transaction. You can easily see this. Hex decoder. If I go here, and I say hex decode. Oh, that's the code. That's a code. I don't want a game. See, is test Ethereum plus 0 padded the rest. And if I were to do this with the attestation type, you can guess what I would get. So if you recall how the FTSO works, so everything there is also hex encoded and 0 padded to provide a specific feed ID. Okay, and this is EVM transaction. Nothing scary. Easy to do in your programming language, already available in the library. Okay, so we have this. We say execute, and we get back this. Okay, so valid. So this is we're now preparing the request. We know what we want to see. We're preparing the request. This prepares a request. We're here. We have a valid status and ABI encoded request. This might look scary, but it's actually not. So this thing here, you can recall it, is just hex encoded attestation type, you see. And then there's hex encoded source ID because data providers needs to know this. Then there's MIC, but here in the end, you can see that here it's exactly our transaction. So it's AE2, this is exactly the transaction hash. So from here on, the data providers can see, yep, this is the transaction hash I'm looking, and this thing here, this is the MIC. So if I hash all this, I should get this as a result, and that's how they check that this is correct. So this is the request body. If I prepare request, let's just quickly take a look at prepare response. Why is that important? Prepare response gives us a result that says, look, this is what you'll be getting after the round is over. So the whole attestation type that you've submitted, but also the whole response body. So this is pretty much everything you can later use. And it's obviously directly according to spec, but you can see what you get. So you see block number, timestamp, source address. It's not a deployment. And this is this bread and butter, events. We can see that events are directly encoded into this. So this is a nice JSON representation that you would like to see and query and use manually. But in a Solidity, you would use something else. But this maps directly to the Solidity structs we have already prepared. Okay, so this is the information. This is the information we see. We've asked the verifier server to do this. Now it's time to push this to the FDC. So now it's time to say, okay, FDC, do it. Okay, so what we're going to do, we're going to go here to the FDC example. So this is the code from Flare Hardhead starter. If you want to start working with Flare, I suggest you start with this starter pack. So it has a few examples. For example, the one that I'm going through now. It has all the necessary libraries already installed, and it has the so-called Flare periphery packages installed, which contains ABIs, additional libraries, everything you need to use to properly interact with the chain and with everything without having to copy them, for example, from Block Explorer, without having to find them, without having to update them. So every time something updates, the only thing you need to do is update your library, and you'll always have the latest ABIs, the latest addresses, and so on. Okay, so I've already deployed this contract. So we're going to skip the first part, and we're going to just go to the second part and prepare the request. So if you recall here, preparing the request was pretty much getting this JSON and submitting it to the prepare request function, and I got back a thing like this. In code, you would do the same thing, except that now the attestation type is dynamically built, because if you can do EVM transaction, you can also do a payment. You just don't want to hard code this immediately. There's test DTH. I construct a request data, which is exactly this JSON. If you can see, it's exactly the same JSON, and the transaction ID, which I've already copied here. So that's the thing we wanna use. And then I pretty much just request this directly from the verifier server. The verifier URL, it's included directly in the environment example, so you can just nicely import it from the process. Okay, so we get this. Let me just run it, see how it goes. Just gonna comment this out so we only get one thing at a time. Yep, that's our request. So pretty much the same thing we got up. And now what we need to do, we need to submit this request to the FDC. We need to submit this request to the FDC contract and say, please, data providers, start working on this. How do we do this? Well, I'm just going to abuse my contract. I'll tell you exactly how. I get the FDC hub at the latest address, wherever it is, and I then request an attestation with exactly the ABI encoded request that I've received from this prepare request. So pretty much exactly what I get from the verifier server, I push to the FDC protocol, and then I'll calculate where exactly is this happening. Why is that important? I'll let you know, because we'll see exactly the process, through the process, what's happening and what's going on. Okay, so I've commented this out. Now I'm going to start preparing the request. So the first thing I do is I prepare the request, I initiate the contract, I get the FDC hub, and I submit the transaction. Boom, and it's done. So the network speed is between a second and 2, so it's very quick. Okay, so I'm going to open this. I'm just going to copy it to have it somewhere else. This is so-called Flare Systems Explorer, which allows you to see what's happening. So let's look at the voting epochs. FDC attestation request. It allows us to see what's happening in the network. So here you see all the requests that were submitted to the attestation. All the requests that were submitted. One of them was ours, TSTTH 1737 my time, which is exactly now. We're going to take a look at this voting epoch. There's been exactly one request, and now we wait for the data providers to firstly notice this request, and in this 90-second period, start to submit their responses. So we batch requests into 90-second epochs, just because it makes it much more efficient, so we can construct a Merkle route out of it. Otherwise, like I said before, we would have a bunch of data points on chain, which is expensive and problematic. While this is happening, I'll come back and refresh this. Let's take a look at how our contract looks. So the contract that you want to use to do it, to do this and to request or to verify all these things is actually pretty simple. So I've overcomplicated it here in the example because I wanted to show how you can get the event info, how you can transfer things and so on. But the main thing is connecting to FDC requires this amount of lines if you have A, aggressive auto formatter, and B, really low line count, a really low column count in your line. In this case, you can see, how do I verify if EVM transaction is valid? So how do I verify if this thing is correct, if the proof that I've gotten from the DA layer is correct? Simple. I get to the contract registry. This is the library already included in the periphery contracts. I get the verification contract, the latest one. So the library makes sure that it always look for the latest one, the one that is approved by Flare. And then the only thing I have to do, I have to verify the EVM transaction. Okay, for the people that are looking, I'm just going to share it, the URL. It's here. It's going to go in the chat. Okay, so this is how you check. And the important thing is, what is this transaction exactly? So beforehand, I was showing you this huge JSON that we're getting in the prepare response. So you've shown this huge JSON. And this is exactly the solidity struct that you would be getting as a proof. This is already included in all the necessary interfaces. So this is the solidity struct that uniquely describes this Ethereum transaction with all the necessary additional information. So this struct for EVM transaction starts with proof. It has a Merkle proof. That's the proof used to verify it, and the data of type response. And response has all this metadata important for FDC, but it also has request body, which is exactly what we've requested to get. So transaction hash and all information. And it has response body, the meat of this data. So things we can use, things that were additionally provided to chain. And this response body has, you see, all this important stuff, but at the end, it has a list of events. And this is the thing that you then use in your contract later in Solidity. So going back, if we take a look at how this really looks, this response body has a bunch of events. And always, 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 when you're doing this, do a sanity check to see if things are working. So we have a list of events. 1, 2, 3. Do they match? 1, 2, 3, 4. Yes, they do. And the first one is from ADBF21. What would that be? ADBF21. Yep, that's exactly the token transfer we're looking for. So the first event matches. The first event is correct. So you can see that you should always cross-check these things to see that you fully understand what you need. Okay, so in the meantime, the round has completed a few minutes ago. So we only had one EVM transaction here, one attestation request. It was confirmed by all data providers on the network. And the easiest thing to see here is to pretty much check that everybody has confirmed it. We have 100% network acceptance ratio. And you can easily check what has happened. Okay, so this was computed in this round. Just a second. So this was accepted by the whole thing. It has gotten into the consensus. And now we can use it in FDC to get all the data. Okay, so we have this round. And now we are moving towards this final step, which is getting the DA layer to get us the proof together with data points. Okay, so we go back to the DA layer. Again, it's available from Flare. It's rate limited. You can use it, but any heavy duty use, you would have to set up your own. Okay. So we set our own voting round in. We execute it, and we get the necessary things in our response. So this time, we get the same response as before with all the same data, but we also get a proof. Proof is empty in that case, just because there was only one attestation required. If I were to go back in time and request a proof for something bigger, for example, for this round, you would see that the proof is larger because it has to prove a lot more things. So for one thing, for just one thing in the, where is that? Oh, here, yeah, it's all right. That one just wasn't finalized. For just one thing in the tree, the proof is exactly the thing you have. For multiple things, you have to go through all the leaves. Okay, so we're here. We know this round. The only thing that's missing is pretty much submitting this to the contract. But before we submit this to the contract, let's see and check what the contract is doing. Okay, at the same point, Swain is asking, why is the epoch 19 seconds specifically? Could it be longer or shorter? The epoch has been selected as 90 seconds because it allows us to have this nice thing between being fast enough for things that are operating on other blockchains and still providing us with an epoch long enough to get batches that are reasonably large. So it cannot be made longer or shorter because it's currently tied to the whole FSP system protocol. We'd have to redeploy the whole protocol and shorten it. We are thinking about making this a bit more efficient and shortening it, but currently that's pretty much the limit. It's imposed by the protocol it ties in. It's pretty much the same length as FTSO scaling has because they're both plugged into the same underlying thing. So yeah, and 90 seconds, well, there are a bunch of numbers you could pick around this time, but 19 was kind of like a sweet spot between doing this very fast and having problems with things finalizing, having problems with things not going through and not being fully deterministic, and having a longer epoch, but waiting longer for things to fall through. Okay, so let's, in the last few minutes, let's check the payment. So the payment contract needs to do, the contract on chain needs to do two things, just two things. First one is you need to verify that the data I'm providing you, the full data I'm providing you, let's check the proof, the full data I'm providing you is indeed correct. So you need to check if this data that has been provided by anyone can provide me this data, is valid according to the FDC. And that's easy to do. So pretty much what you do, you go to the contract registry, get the verification and verify. And now you're done. You're sure that the data is correct. The next thing you need to do is your application business logic. So what do you do then? Well, in your application business logic, you do whatever you need to do. In our case, we're going to go through all events and check which ones are the ones that are important for our contract and save them. So we're just going to save them because that's the easiest thing to do. In your case, you could say, okay, I've seen that you've paid me on Ethereum. I've seen that you've made a swap on Ethereum. I've seen that on Ethereum, you have invoked these specific functions, which, I don't know, transfer the ownership of the contract to me, which means that I'm also going to transfer the ownership of contract on Flare to you. I've seen that you've breached something on Ethereum, you've locked it. I'm going to issue you something here. So this thing here is your business logic, and it's constrained pretty much by your imagination and gas limits of the solidity. So gas limits of the underlying network. But the gas limits are not that restrictive, so it's mostly the imagination about what you can come up with. Okay, and here we just do a simple loop over all events. We gather the events out. We check that these are emitted by the correct event. So, and our event would be that one. Beware, even though I call it USDC, it's not USDC, it's some other address, some other token that acts like a token. And then I check that the topics match. Then I check that, then I pretty much withdraw everything out. So I get the sender out of topics. I get the receiver out of topics, and I finally decode the data. How do I decode the data? I decode the data because I know exactly how the data should look because of the topics, the topic with index 0, which tells me how this event is structured. So like I said before, there is a question, can I be doing this on any other chains than EVM? Ethereum, maybe non-EVM. So currently with these types, we only support EVM. You can do this on other EVM chains very easily. So we can easily connect other EVM chains. Non-EVM chains are not yet connected, and they can be a bit problematic because before we connect chain, we really want to make sure that these requests are deterministic. So there's no way to induce a problematic request that might impact the consensus. And secondly, you want to make sure that these requests are generic enough to cover a large amount of use cases. And then the third thing is, once all this is done, we need to make sure that our validators are properly observing other chains. They don't need to be validators on other chains, but they have to observe them. And to properly observe them, they need to integrate all the nodes. And there's some security assumptions here, and there's also some costs associated with this. So the main point is you want to have a decentralized way of looking at other chains, and integrating other chains means getting the validators to run nodes from other chains, which is sometimes quite expensive, but sometimes it's cheap. Depends on the chain. So those things are really, really chain dependent. So EVM for EVM transactions, and all the other attestation types for Bitcoin, Dogecoin, XRP currently. And as I said, we're extending this to Web2 data sources very soon. Okay, so we have an event, we have a contract that gets all events, pushes them, and that's it. And now the only thing to really see is to check how do I finish this. So if I go here, and like I said, so this was completed in this specific round. The only thing I need to do is pretty much make my script. This is the verifier, and this is the DA layer. The only thing I need to do is make my script go to that round, get this proof out, and push it to my contract. So what am I going to do? Well, just execute a code that does this. This is this final round of code. Let me just check. Okay, so everything is commented out. And this is this final round of code. So I get the proof, prepare request, DA layer, get the proof round data, ABI encoded request, round ID, and let's see what proof I get. And this, proof, and I get the same thing as I got here manually. Should be. Okay. And to really, really finish this, the only thing I now need to do is to submit this proof. So again, get the proof, instantiate my contract, and just call this collect event function that I need with the correct data. And don't worry, we've made sure that the data matches. So whatever is returned to you by the DA layer is exactly the thing that you have to push into contract, and is exactly the type, solidity type that comes from all the necessary things imported in the periphery package. And that's exactly the type that you push directly to the verification contract. So you don't have to match anything somewhere. You don't have to do any post-processing. This is already correctly done by all the tooling. Okay, so what do I need to do? I need to change this, I think. I'm just going to submit this. No, this is not going to work because I have to invoke the function. Let me run this. That's it. Oh, and I get this. So submitted the proof, and let's check the transaction. So I've deployed this contract before and tested it just to make sure that no live demo, no live direct demos. So this is the transaction. It interacted with my transfer event listener. You see that the data that I've provided is actually huge, but actually, if you take a look at it, it's already easily transcribed and already easily decoded by the Explorer just because I verified the contract, and the rest is pretty much direct. So this one goes through nicely. You can check it here, although you might not want to, but this is just ABI encoded version of this thing or this thing here. Okay, so I got this, and if I were to check the contract itself, you see that this was submitted correctly and something was submitted correctly 2 hours ago. But if I were to go to the contract itself, I could now interact with this token transfer list and get things out, explore them, see them, issue something on top of them. Okay, cool. That's pretty much it for today. So that's how you use FDC. It was a short introduction, pretty much with a lot of information. So I hope you didn't die in between. But yeah, I've shared some links in the chat. You can check them out. There's always the Dev Hub, and yeah, happy coding.
Absolutely, happy coding to everybody. Do we have any further questions from anyone? In the meanwhile, Filip, perhaps you can share your socials, maybe a Twitter account or anything else where people can reach out to you if they have any questions later on.
So let me just get my Twitter account somewhere. So here's my Twitter. The easiest way is to get me on Telegram, where I have the same. And yeah, that's the easiest thing to get into in touch. There's also a Discord we're running, so you can ask questions there. Anthony is taking care of them. So yeah, if you have any other questions, if you want to develop, feel free. It's an EVM layer 1, so you've seen all the existing nice things, but what we really have is this data connectivity and the ability to do stuff.
Perfect. Thank you very much. I think this pretty much brings us to the end. We have technically 5 more minutes left, but this is a good place to cut the session off. Thank you very much, everybody, for coming and for answering, for asking all these questions, and thank you to Filip for answering them as well. We will see you on Monday for session number 7, where Filip will be continuing his overview of the FDC. Until then, have a lovely rest of your day, and see you all on Monday at the same time.
Okay.
Bye-bye.
Bye.